Newton's second law, the sum of the forces is equal to the mass of an object times the acceleration of an object. The rotational analog for Newton's second law is right here. The sum of the torques is equal to the moment of inertia of the object times the angular acceleration of the object. We'll go ahead and define those terms here. The units for torque are, of course, Newton meters. Moment of inertia, as we know, is kilogram meter squared, and angular acceleration is radians per second squared, just like linear acceleration is meters per second squared, angular acceleration is radians per second squared. So, there is a distinct similarity between these equations, just like there was a similarity between linear and angular momentum and linear and rotational kinetic energy. So, let's do a problem. We've got a football player who applies a torque to a football, and the football has a moment of inertia that's given here. And if the football starts from rest, in other words, if it's not rotating, what's the angular acceleration of the ball as the QB throws it? In other words, when it leaves his hand, at what rate was it accelerating while it was beginning to speed up? So we're going to sum the torques, and we're going to set that equal to the moment of inertia times the angular acceleration. Well, this is a fairly simple one. We're given the sum of the torques, we're given the moment of inertia, so the angular acceleration is simply 140 radians per second squared. Let's try a problem that's a little more challenging. Here we have a CD with a certain mass and a certain radius. Our problem says that it starts from rest and speeds up to 220 RPM in 1.6 seconds, and we want the net torque that the disc player applies to the CD. So what we want to find is the left side of this equation, the net torque. To do that, we need the moment of inertia of the CD, and we need its angular acceleration. So let's find each of those two quantities, and once we have those, their product will be the answer, the net torque that we're looking for. So the moment of inertia of this CD is simply based on the geometry of the CD and about which axis it's being rotated. So if we consult a table of moment of inertia equations, we'll find that a disk rotating about its central axis has this moment of inertia, 1/2 mr squared. But we remember that the mass and the radius have to have particular units. And what are those units? In SI, mass is kilograms, and radius, or distance, is best expressed in meters. So we need to be a little careful here because the mass of the CD and its radius are not given in the proper units. So I haven't shown that work, but I trust that you can convert 8 grams into kilograms and 6 centimeters into meters. The product of those numbers is the moment of inertia I that we're after. So we have the moment of inertia figured out. Now we just have to figure out the angular acceleration, and then we'll be able to multiply those to get our net torque. So the definition for angular acceleration is change in angular speed divided by change in time. So that numerator, change in angular speed, is simply the final angular speed minus the initial angular speed. This CD starts at rest, so its initial angular speed is 0. And we're told that its final angular speed is 220 revolutions per minute. Here again, revolutions per minute is not the proper unit for angular speed. we want to change this into radians per second. So, change the minutes into seconds first, and we've oriented the conversion factor like so, such that these minutes in the numerator cancel these minutes in the denominator. Then we need to convert revolutions into radians. And what's that equivalency? 1 revolution is 2 pi radians. And again, we've oriented this conversion factor such that the revolutions in the denominator will effectively cancel the revolutions in the numerator. You can see we'll be left with radians in the numerator and seconds in the denominator. 23 radians per second. That's the final angular speed. So the acceleration, the angular acceleration, is the change in angular speed divided by the change in time. Let's go ahead and show that. There's our moment of inertia we calculated earlier, 1.44 times 10 to the negative fifth. The angular acceleration is omega final minus omega initial divided by delta t. 2.1 times 10 to the negative fourth Newton meters. Let's summarize. In this lesson we discussed the rotational analog of Newton's second law, which we earlier learned was the sum of the forces is equal to the mass times the acceleration. The rotational analog is the sum of the torques is equal to the moment of inertia times the angular acceleration. We did one straightforward example problem, and we did another example problem, more complex, that required unit conversions and an intermediate calculation based on the definition of the angular acceleration alpha.